sponsor. Thank you again for your help to organize this very nice conference with your help. So, Mrs. Miss Sandra Tuță from Avantor.
Thank you very much for the opportunity. I think this is again also for us to participate in such a thing because it's a small contribution that we give back to the research world. So, which is Avantor? We have some small issue, technical issue. So I will speak about Avantor. Avantor is a corporation, worldwide corporation that joined with VWR, like also it's a worldwide corporation. And they decide to go together under brand Avantor. Why? Because they want to be as a complete supplier for all goods, also for chemicals, also for start with research, QC lab, and go to the scale up business, or even to the production business. They are mainly go to the biotech and high quality industry like aeronautics and so on. But the main goal for us is the biotech industry. So because we are close together and do work together, I will present today a little bit marketing, and after that I will go to our research team, which is located, research team for chromatography, which is located in England. They are a very strong center because in 2017 Avantor VWR bought a High-Chrome company, which is a very old company with a history in chromatography. More than 15 years. They develop new chromatography phases and so on. So I will go to the sample prep because I will, now those days, they're very important to pay attention to the sample prep. Why? Because the sample are matrix complex, more and more complex matrix. So it's important because the error that bring in your analyze or in your research, the sample prep is bring about 80% of the error. So, okay. As I told you, I represent Avantor. I told the short story, please. Okay, we are overall in the world. Our goal is, as I say, the biotech company and develop. By the way, we close together with Moderna and Pfizer on mRNA COVID development with our supplier, as a supplier, but also as a technical advisor for Moderna in US. So starting with research and discovery, develop, scale up, manufacturing and delivery. Actually, we have iCare value, which is innovation, customer-centric, the rest of regarding fiability on the market, accountability, respect, and excellence. I will put action on innovation because I will go to a research that our central does, as I told you already. Quality, I think quality is very important, including in research, because you need to have something to get and to exclude the error in your research. When you do public some paper, this is important to use quality reagent, quality product. Okay. Now we go the interesting part that is innovative in Avantor and optimize sample preparation for environmental analysis. Why environmental analysis? Because those days they're I don't know, a big topic on that and try to be more and more involved in that. For sample preparation, you use syringe filter, centrifugation, CPE, more or less. I put even a QR bar if you want, and you are interested, you can just, push it and see what is the plan. So study case, what the study of analysis of polyfluoroalkyl substance. Why? Because they are very present in the plastics, and they are basically everywhere. And a recent study decided they are they are linked with poor antibody reaction curve or kind of cancers, kidney, for example. And EPA and WSPA, the agency, they decide to monitorize that. But we have a really issue in that, because they are present in the laboratory environment, and also they are present in the tubing and so on. But the limit of detection is very low. So this could be a problem. So more or less, our researcher that decides to go to the EPA method that is mentioned there. So they try to analyze the system that the analysis is described here, the condition for the chromatography, what is in a ultra core column that we produce, of course. So they saw it's very hard to distillate which is the probe and which is the contamination. That is because the low limit of the compound. So they start to test from which part the contamination become, and they test all the LCMS system, because the detection is so low. We use a LCMS system. So they try to find every component if they are free of polyfluoroalkyl products. But in the end, they determined that each component, including the vials, the PP cap for the vials, can be a point of contamination, the solvent, the injection, everything. So what we can do in this case, in this case, they decide to put another column that the delay the product. So they put a column before injection, inject through the column. That's the way they obtain, like can be seen in, in this slide. They put a column before that can decide what to eradicate the contamination. Yeah. So the peaks go with some delay. But I will go further very fast because I don't want to take. So the sample preparation filter, it's important which filter you can use because the particles, do you know that? It's but also it's important from the point of the extractable, because the filter is made from some materials. The materials contain a lot of things, and sometimes that can be influenced, and you see the influence, what is regarding the filters, coming from the filters, no? See? CPE, this is the most common phase in environmental. They use a lot in environmental. This is all steps. What can be done to have a good application of CPE? What do I choose? I need to choose the sorbent. I need to choose the perfect solvent, depend of the phase. I put it here. It's easy. Okay, that I want to mention. We have a special device that name is spin disc, which is the same CPE, but the chromatography phase, it's compressed between different filters, which is deep filters, just for particles, okay? But what does mean this? This means for you a higher flow rate, a higher capacity. It go through 5 liters versus if you want to concentrate, especially for the kind of application, if you want to concentrate a big sample, you need to use, we have a different speed disk, is not so small, it's a bigger one with for 5 liters, up to 5 liters. high capacity, minimum of clogging. Why? Because they are compact. They also be they will use less solvent. That and this is our resources, because we like to share all our discoveries, or not all mine, because VWR is it's a complex. It's you have webinars, you have access on the webinars, you have access on application, even in life science or chromatography or in chemical or so on. Because we work together in science to build a brighter future. So thank you for my side. I was sharp. If you have question, I'm open for you to listen and to answer if I can. Because if I can't, I will put the question to our team. That I will thank you, the team from Anthony Edge, who develop all this. Thank you.
Thank you very much, Sandra. I want to ask you, the access for the webinars is free.
Also for the application protocol, you have a lot of things there. You can search the application. If you want, we can do something to show all the researcher.
Yes, maybe one of the next events.
Yes, of course.
We
in
can
December.
make like a training course.
How
to access and how to.
It's very useful. I have always I do that, because I think it's very important, especially for young researcher, to have access on this kind of technical database, because that it is. Thank you.
Thank you very much. If you have questions from.
Hello and welcome, Sandra.
Thank you.
How big is this equipment?
Which one?
The chromatographic one, because you before, and not only.
We don't put in Romanian market chromatographic equipment. No, they work with for this. They work with Agilent. MS. Yeah.
Yes.
We have high chrome, but high chrome.
We spoke before, and we want, because we wanted, we were interested also, as I explained to you, for the validation of our sensor for smaller device.
We can discuss to find a solution.
Yes.
With our partners.
I wasn't from the beginning, because we were in an workshop and I thought that you presented us. Oh, sorry.
No problem.
Congratulations.
We can arrange that. Thank you. Yeah. No.
Thank you. Where can we find the Romanian contact information?
Here.
Okay.
No. In Romania, we are like this. We work through distributor and work also directly through Austria. We have 3 sales people and 5 people on quotations. They say like that, but they are highly knowledge and technology, so they can use. Yeah, only distributors. But if you need technical information, if you need, you can contact me.
So you don't directly provide?
No, that's very no. But also you can buy in euro from Austria. No, I'm joking. I'm joking. Yeah. No. For technical support, I can do some, and if I can't, I also.
Okay, we will discuss.
Yes. Thank you.
Thank you very much.
Thank you.
Other questions? Okay, thank you very much, Sandra. And
thank you for your kindness.
To have a long collaboration.
No, thank you.
Good morning, everyone. I would also like to thank our sponsor, Sandra Tuță, for her presence today. We will start our presentations right now together with my colleague, Cristina Ineșcuță, will chair this session. So the first presenter is Maria Grapin with the work entitled Studies on Photocatalytic Degradation of Methylene Blue using TO2 transition metal oxides heterojunction.
Hello, everyone, and welcome. My name is Maria Grapin. I am a research assistant in team number 10, and today I will present you my paper entitled Studies on Photocatalytic Degradation of Methylene Blue using titanium dioxide with transitional metal oxides heterojunctions. The rapid progress of global industry has led to environmental pollution and in particular to wastewater generated from textile industry containing different organic dyestuffs, and by their degradation are able to form highly toxic and carcinogenic compounds. Advanced oxidation can solve this problem by creating reactive species following solar irradiation, which is an efficient and sustainable technology for removing non-biodegradable contaminants. The abundance of non-biodegradable contaminants in aqueous effluents have led to their inefficiency of their removal. Therefore, the aim of this work is to examine the photocatalytic degradation of textile dye methylene blue using titanium dioxide doped with various metal oxides. Starting with the principles of the photocatalysis, Figure 1 shows a schematic illustration of semiconductor photoactivation and electron gap pair generation. Photocatalysis on semiconductor photocatalyst involves three main steps. Step number 1, irradiation of light with energy higher than the semiconductor band gap will lead to generation of electrons in the conduction band and holes in the valence band. Both electrons and holes migrate to the semiconductor surface. The photodegenerated molecule oxidizes water molecule to form hydroxyl radical, while the photogenerated electron reduces dissolved oxygen to form superoxide radical anion. The formation of superoxide radical anion and hydroxyl radical with high oxidation potential can degrade organic pollutant into readily biodegradable products. As for metal oxide semiconductors, they are promising candidates for photocatalytic application due to its light absorption properties, charge transfer characteristics, lifetime of excited state, and electron structures. But they suffer for inefficiency of non-absorbing visible photocatalytic light. Therefore, to overcome this disadvantage and to improve a photocatalytic response in visible light, coupling metal oxides with other metals has been used. In this study, we used titanium dioxide as support due to its high level of activity in many photocatalytic reaction systems. The schematic synthesis of our metal oxide photocatalyst is shown in Figure 2 when titanium dioxide, sodium carbonate, and metal ions were mixed with the ethylene glycol, the mixture being stirred well dispersed. The synthesis was carried out in a discovered 2.0 microwave flow reactor at 160 degrees Celsius for 10 minutes. After the reaction, the solution was subjected to mixing using stirring systems, followed by a filtering, drying, and calcining stage to obtain metal oxide photocatalyst. In order to determine which metal ion is more effective, 6 samples were performed, as is shown in Table 1. As an application, we have chosen to present the photocatalytic degradation of methylene blue from aqueous effluents. Methylene blue is one of the widely most used industrial dye. And for this purpose, the synthetic photocatalysts were mixed with a styrene acrylic film forming material and deposed on a glass plates. The photocatalytic activity was evaluated by xenotest lamp. In terms of results and discussion, Figure 5 presents some images of titanium dioxide photocatalyst nanoparticles doped with iron, nickel, and manganese, which have been used to test the photocatalytic performance. The photocatalytic nanoparticles formed are highly agglomerated, and also they are visible in spherical shaped particles and clambed distributions. As for spectrophotometric analysis, Figure 6 presents reflectance spectra of the synthesis materials, which present the absorbance of metal oxide photocatalyst in visible area, while titanium dioxide present absorbance only in UV area. The evaluation of photodegradation of methylene blue solution was recorded and are presented in Figure 7, where titanium dioxide doped with iron present the best results photocatalytic degradation, because it registers the best obstacle for the recombination of electrons and holes. In conclusion, the present work shows the improved photocatalytic properties for photocatalytic degradation of methylene blue using titanium dioxide doped with transitional metal oxides compared to titanium dioxide. The preparation method of photocatalyst is simple, cost-effective, involves low temperature, and require a short reaction time of preparation. The results show that methylene blue dye is decolorized throughout degradation. Titanium dioxide doped with iron present the higher photocatalytic performance. And in order to evaluate the composition of the effluents after degradation, HPLC-MS and chalk analysis will be performed. In the future, we aim to optimize the synthesis process by achieving more effective coupling by finding the right metal oxide interface. And last but not least, we acknowledge the support of Ministry of Research, Innovation and Digitalization, who made this work possible. Thank you for your attention.
Thank you very much, Maria. Very good, nice results. So if we have any questions from the room? Yes.
The kinetics of degradation is a little bit slow. What kind of strategy are you thinking to improve the time needed to degrade the methylene blue or other molecule? Because you need 200 minutes to full degrade the methylene blue. So is this for practical application? It's not possible. It's too much time. Do you have an idea?
I'm not sure. I don't want to give you answer. I'm going to research about it, and thank you for your suggestion.
Okay. Well, I just say that probably with your new synthesis, you can reach a faster kinetic degradation. So probably that will be the answer.
Okay, thank you.
Thank you. If we have any other questions from the room or comments, or from the online participants? No. In this case, thank you, Maria.
Thank
Yeah.
you.
Hello, everyone. We continue with next 5 oral presentation. So we invite Ioana Popa-Tudor to present us the difference and similarities of acid extracted lignin versus extracted lignin. Ioana, maybe? Tudor? Ah, scusa, sorry.
Hello. Welcome to my presentation entitled Differences and Similarities of Acid Extracted Lignin versus Des-Extracted Lignin. The green chemistry was initially developed because the Pollution Prevention Act was important for the new green opportunities for processes and recycling byproducts and biomaterials. The green chemistry approach seeks to redesign the materials that make up the basis of our society and our economy, including the materials that generate, store, and transport our energy in ways that are meaning for humans and in the environment and possesses intrinsic sustainability. Lean biopolymers is a big heteropolymers which contains three main precursors, para-coumaryl, coniferyl, and synapyl alcohols, which form para-hydroxyphenyl guacyl and syringyl units that form the 3D structures of the lignin. The main benefits of lignin in the plant protects hydrophilic components, confers protection shield against distortion and compression, ensure mechanical resistance, and due to the antioxidant activity, she was propelled in pharmacological and phytotherapy domains, and in biological field to try obtaining biogas material. Brewer spent grain is the major byproduct of the brewing industry. It is a rich source of cellulose, hemicellulose, and lignin, and the other compounds such as polyphenols. In the last years, many countries adopt introducing the brewer spent grain in the food industry and in agriculture as into animal feed, but not least this interest were high in energy industry as a possible source of biogas. For obtain lignin, were necessary several steps, the grinding steps, the removal of extractables from BSG, and the applied des were the applied des proof the commercial solvent or the commercial solvents can be applied in extracted lignin. The main components of BSG are cellulose, hemicellulose, and lignin. We obtained a percent of 90.2 in our work. The synthesis of this is simple, feasible. The melting point reached only 60 degrees compared to the main precursors, and it is known that a diputectic solvent is composed of two main components: hydrogen bond acceptor and hydrogen bond donor. In our case, choline chloride is a hydrogen bond acceptor, and lactic acid is a hydrogen bond donor. For this characterization, we use TI Fourier transform infrared spectroscopy. The spectra of this present the bands which correspond to lactic acid that were preserved in this, but with some shifted due to the formation of hydrogen bonds. Also, there are specific choline chloride bands involved in the formation of this. Compared with water, the surface tensions of this is lower, and the densities are higher due to the formation of hydrogen bonds in the structures. We used to extraction method, acid extracted lignin and this extracted lignin. These two methods are different with different reaction conditions. I want to present you a short demonstration of extracting lignin with diputectic solvents. The raw material is treated with diputectic solvent. And the lignin leaves with this, and the residual product is BSG post-extraction. For lignin quantification, we use spectrophotometric methods. The characteristic wavelength of lignin were 280 nanometers. These two spectra have much more similarities. And this method was compared with gravimetric analysis. And there are comparable results. For characterization of this extracted lignin and acid extracted lignin, we made a Fourier spectrum. The band corresponding of a hydroxyl group is present these bands correspond to carbon-hydrogen bonds which are present in the propenyl groups attached to the structural units of lignin. In this region, we can see the stretching vibration of aromatic ring. This band correspond to guaiacyl units predominant in commercial lignin. And this band corresponds to syringyl deformation predominant in this extracted lignin. In conclusion, this can compete with commercial solvents in lignin extraction. The Fourier transform data of these two lignins show characteristics band given by the vibration molecules specific for structural units. Some bands are suggestive of syringyl and parahydroxyl phenyl units. Gravimetric and UV-Vis analysis show the quantitative similarities. The variations of the two lignins were given by the different way of degradation and the extraction solvent applied. And at least, not least, I want to thank you for your attention. Thank you.
Thank you, Ioana, for your presentation.
Thank you.
So, if any question, okay. Thank you. For the next presentation, we invite Farouk Usman from online, from Department of Energy and Applied Chemistry from Nigeria, to present us his work. Farouk?
Yes, yeah.
Is this online?
Yes. Can you see my slides?
Hello, we hear you.
Okay. Can you all hear me? Can I start? Hello?
It's okay. Please.
All right.
Farouk?
Okay. My name is Farouk Usman. I am a PhD student from Usman Danfodio University, Sokoto, Nigeria. We had to present on the oxygenation of Jatropha cactus oil to hydrocarbons using nickel oxide doped on aluminum pellet clay. The energy crisis that is associated with fossil fuels has necessitated development of several catalytic methods. For example, here in Nigeria, the president just announced the removal of subsidy from PMS, and that has plunged the country into unexpected economic crisis due to that. So there is a need for development of an alternative, and that alternative, among those alternatives, is the conversion of triglyceride to hydrocarbons directly. Several catalysts have been used, just like PT and PD, but as you know, they are noble, they are expensive. That is why we try to look at a group of smectite clay, which is montemorillite, because we found it's an acidic material and can perform in this kind of catalytic conversion. But this catalytic activity of the bentonite or montemorillite can be improved by a process called pillaring. This is the diagram showing the how the pillaring take place. You have the aluminosilicate layer. In between them, we have the interlayer cations. When you introduce, in our case, that we're introducing aluminium, to replace the interlayer cations, do the intercalation, and after you calcine, you'll get a pillar. By doing that, you can increase the thermal stability, you can increase the porosity, you can increase the surface area, because the despacing will increase, and that will translate in the increase in surface area. So in this research, we look at inexpensive nickel oxide doped on this aluminum pellet clay. We prepared, characterized, and tested it for the conversion of Jatropha oil to the hydrocarbons. This is the materials method. Bentonite, the Jatropha cactus oil, sodium hydroxide, aluminum chloride, all the metal precursors of the nitrates. The bentonite will be converted into the pellet clay. We first prepare the pillaring solution, which is the relation of NaOH and aluminum chloride, and then we mix it with 5% clay suspension. After the intercalation, we calcine at 500 degrees for 5 hours. We obtain the pellet clay. Then the methyl oxides were doped onto the aluminum pellet clay using the impregnation method, and we prepared it in such a way that it will give us the 20% metal oxide on aluminum pellet clay. The bentonite, the prepared pellet clay, the metal oxide doped on aluminum pellet clay were all characterized using FTR, XR, XRD, BET, pyridine absorption, and in some cases we have already to characterize them, their swelling index and loss of ignition. And also, the Jatropha coccus oil before their action was subjected to GCMS analysis for the molecular profile, physicochemical analysis, and elemental analysis. And then each catalyst is with 10 grams of Jatropha coccus oil, 5% weight catalyst at a temperature of 380 degrees for 1 hour under continuous flow of nitrogen. In this case, we did not use any external hydrogen. And when the liquid product were obtained, we subjected them to GCMS analysis to find out the molecular profile. Then this is the result for the physicochemical analysis of the Jatropha coccus oil. You can see the density is 0.89 is appreciable. You can see the iodine value is over 100, and then that might be due to the unsaturation in the oil. You see high heating value of 39.7, and this can be improved. You have a saponification value of 198, telling us the amount of saponifiable fatty acid in there. And this is the result for the elemental analysis. We find out the carbon is around 76% with hydrogen and oxygen nearly the same. Then the nitrogen of 0.3%. Our concern here is the oxygen to carbon ratio. We expect at the end to reduce this oxygen to carbon ratio after the oxygenation. This is the molecular profile of the Jatropha coccus oil with palmitic acid 20%, with linoleic acid 61%, and then stearic acid 8.77%, and also with oleic acid. This is the how we divided it into saturated, monosaturated, and polysaturated. So in all, the degree of saturation is around 68.756%. So that means oil is highly saturated, and it is going to affect the liquid product we're going to obtain. And then here is the crystallization of the bentonite and the aluminum pellet clay. For the swell index, we got 92.8%. And then for that of aluminum pellet clay, we got 78.53. And this is due to the replacement of the interlayer cations that are in between the aluminosilicate layers because they are responsible for absorption of water. After the pillaring, that means replace some of the aluminum 3+ was able to exchange with the calcium, magnesium, and in some other cases, sodium. This is the elemental composition of the bentonite and all other catalysts, aluminium, alumina, and silica, which are the main constituents of the metamontrolite been observed. Then we have calcium, which is about 5.20. So because of that, we don't even have the presence of sodium. So we classify this bentonite as a calcium bentonite. And the high percentage you are seeing in nickel is because of the 20% nickel we added onto the aluminum pellet clay. And also you can observe that after the addition of the pillaring solution containing aluminum, the amount of aluminum oxide there is have significantly increased compared to samples. Then this is the summary of the absorption bands that we get. So it's telling us here in the bentonite, in the aluminum pellically, in the nickel oxide, we all have the absorption bands have appeared in all the materials, telling us that even after the pillaring and even after the doping of the metal, our main structure is there. But there is a difference in the intensity of the absorption bands on the FTR. For example, here in the bentonite, if you look at the at 3-4 here compared to here, there is a little increase in width, and this is calculated at the due to the incorporation of the aluminium as a pillar, and also there is a reduction in here in the SiO and the here and the ALO, and this can be due to the interaction between the incorporated metal and the alumina and the aluminum and silica in the tetrahedral or octahedral sheets. So here is the result of the XRD. So for as explained in the introduction, you cannot have our target is to our target is to increase the surface area. You cannot increase the surface area until you increase the D-spacing. So you can see here from the basal D-spacing of 12.45, we are able to increase it to 17.07. There is a shift of the 2 theta value a little bit backward from 7.10 to 5.3. So this have confirmed that we have increased the spacing. So this is the BET result for the surface area, the pore volume and the pore diameter. You can see here from 173.955, we are able to increase the surface area to 385.869. But as we impregnate nickel oxide onto the clay, the surface area decrease. But still, compared to the bentonite, it is still a significant increase. Here is the FTR is the pyridine absorption in continuation with FTR. The bands are around 140 and around 1595 corresponding to the Lewis acidity, while the ones around 500 is corresponding to the combination of Lewis acidity and Bronsted acidity. Here we did that. We did not quantify the acidity, but we did that to make sure we have seen the acidic sites, the Bronsted acid site, and they are there in all the bentonite, the aluminum, clear, and the nickel oxide. But there is an increase in the Lewis acidity, and is expected when you introduce a metal oxide onto the clay. There should be an increase, and here is showing us the absorption bands have increased, suggesting an increase in the Lewis acidity overall. The Bronsted and the acidic the Lewis acidic sites present in all the materials. So here is the result, the mass balance of the products after the reaction. The 10 grams here, we got the liquid product of 3.2 in the blank. We got the liquid product of 3.0, but in the case of nickel, we got the liquid product of 5.03. Overall, in an ideal deoxygenation reaction, we're supposed to get around 68% of these liquid products, and we are not expecting to have a char and residue. But this is among the downside of the oxygenation, because we are using jatropha oil, which consists of many types of fatty acid. Irrespective, in some other cases, you use model compound. So the presence of char and the residue is due to the aromatization, polycondensation, and other many reactions alongside the oxygenation reaction. So this is the liquid product selectivity for the hydrocarbons. If you look at for nickel, it has reached up to over 50%. But still, we still have carboxylic acid, we still have alcohol, we still have ketone aldehyde, and also unreacted ester. So the fact that the nickel got the highest hydrocarbons, it seems that it is better than aluminum pellet clay, and it's also better than the blank that we just use temperature. So it's confirming that there is need for the catalytic information. And here is the type of the hydrocarbons present in the products. We have alkanes, we have alkenes. If you can remember, in our molecular profile of hydrocarbons oil, we have almost 68% of the unsaturation. So that is the reason we're having so many this high amount of alkenes and less amount of alkanes. And another issue is that as the alkanes can be from the carboxylation, and these alkanes can improve from decarbonylation. We still have cyclic compounds and aromatics, and it has been reported that these reactions also take place alongside the oxygenation reaction. And then we try to compare the biogasoline and green diesel selectivity of the product. So if you look at for the aluminum pellet clay, it's around more than 50% biogasoline. This is telling you that the amount of the processed acid and the cracking ability rather than the oxygenation pathway is predominant in aluminum pellet clay also. But there is a near equal percentage of biogasoline and green diesel when we use nickel oxide. And this is telling us that the deoxygenation has taken place, but also cracking. It's another pathway followed for this oxidation. And it's unsurprising because nickel have that cracking ability. So in conclusion, the pellet clay and the metal oxide doped pellet clay were successfully prepared and characterized. So the nickel doped on aluminum pellet clay has shown the oxygenation activity to produce up to 51% hydrocarbons. And then the nearly equal percentage of biogasoline and green diesel in the product are indication that both cracking and the oxygenation of non-fatty acid as a cause. In our future work, we are going to try to optimize this process. We try to also change the metal loading from 20% and vary it to see what is going to happen. And also we intend to use other metal oxide to see if we can improve the hydrocarbons in our liquid products. Thank you for listening. Thank you.
Thank you, Farouk, for your nice presentation. You have a lot of results. So if anyone say something or any question? No? Okay, thank you again. So we continue with Livia Teodora Ciobanu and his work.
Okay. Hello, my name is Livia Ciobanu. I am a research assistant in Team 4 Bioproducts here at PRIOCHEM. And today I am going to present to you a sustainable approach towards management of brewery waste, specifically spent brewer's yeast. I'm going to describe a little bit about streamlined ultrasonic lysis method. And I'm going to highlight how optimal parameters might generate bioproducts with elevated bioactivity. As we all know, sustainability is more important now maybe than ever. It should be included in our daily habits. It should be included in every industrial process. So it is crucial to know how to spot the value even when it comes to wastes. When it comes to spent bioresist, its valuable properties speak from themselves. Yeasts are known to be great probiotics. They're basically bioactive pools of compounds with immunomodulating activity, antioxidant activity. This reveals their potential to be used as functional ingredients in both animal and human foods. Besides their applications in the food industry, they are great enzyme sources. They can even be used to produce biofuels in a sustainable manner. They can be used as bioabsorption agents if we take into consideration the property of yeast cells, and so on. So the question is, how can we exploit to the furthest extent this pool of bioactive compounds? A practical answer would be yeast cell lysis. There are many methods to disrupt the cells, but we chose to focus on a mechanical method, on ultrasonication specifically, because it is a low-cost method. It doesn't require, it requires minimum equipment. It doesn't require any chemical reagents that might interfere with further biomedical applications, and is overall simple to perform. The principle of ultrasonication relies on the capacity of ultrasound waves to cause the formation of certain gas bubbles inside a cell that will continuously pop and will cause pressure that will eventually disrupt the yeast cell wall and will cause the release of the intracellular compounds, which is, of course, the target of the experiment. So we proceeded to test important ultrasonication parameters to find the optimal yeast cell lysis conditions. We started with testing the influence of sample concentration on lysis efficiency. So of course we prepared spent bioresist samples of different concentrations. We selected the concentration which we considered ideal for lysis, and we proceeded to prepare 2 sets of samples with the optimal concentration using a 33.43% duty cycle for set A of samples and a 50% duty cycle for set B. In each set, the processing temperature ranged between 40 and 70 degrees. Each sample was finally centrifuged to obtain the yeast derivatives, specifically the yeast extracts and the yeast cell walls. We primarily evaluated lysis efficiency by assessing the protein content of the yeast extracts through Biuret method. Why? Because a high release of intracellular proteins means an efficient lysis. So the first picture shows the protein content of the yeast extracts obtained from samples with different concentration of spent bioresist, and it can be observed that there is almost an inversely proportional trend of sample concentration to the protein content of the yeast extracts. So basically the most diluted sample was the one that was the most efficiently lysed. The second image shows the samples with the same concentration, the optimal concentration, but the duty cycles and the temperature are varied. There is a certain descending trend with temperature. The protein content of the yeast extracts in the duty cycle of 33% decreased with the increase of temperature. However, overall, the lysis was the most efficient at 40 degrees at a 33 duty cycle. Because high temperature can influence, can denaturate proteins, can cause precipitation, and could interfere with the data obtained through the protein content of the yeast extract. We decided to test an additional assay method for lysis efficiency. So disruption efficiency was assessed using a gravimetrical method, which quantified the loss of dried biomass during lysis. This data confirmed the previous results, showing that there is indeed an inversely proportional trend between sample concentration and temperature. The lysis efficiency decreases with the increase of temperature and with the increase of sample concentration. Optic microscopy was used to analyze the spent pre-resist cell lysis. An optimal sample was assessed. The yeast cells were stained using methylene blue. In the first image, the unprocessed intact cells can be observed, in contrast with the second image, which shows the lysed cells. The intracellular content is released. It forms aggregates. It still retains the methylene blue stain. In the third picture, it can be observed the yeast cell walls collected after centrifugation, then after the supernatant was discarded. Yeast cell walls appear as almost round-shaped white circles. There are, of course, also some intact cells still. Scanning electron microscopy was also used to observe lysis efficiency. We assessed the same optimal sample prior and after lysis. The prior lysis, the cells can be observed are morphologically normal, are intact, and the third and the fourth picture show the obvious breakages in cell membrane, and the disrupted yeast cell walls can be observed. So basically, scanning electron microscopy confirms that lysis occurred and it was efficient. Spent Brewer's yeast cell walls were characterized by means of Fourier transform spectroscopy and beta-glucan content. The spectrums of raw biomass of spent brewer's yeast, of the spectrum of the optimal sample, and that of yeast cell walls obtained from the optimal sample were assessed. The spectrum of the raw biomass presents mostly bands characteristic for yeasts, characteristic, for example, for hydroxyl and NH from hydrogen bonds, for methyl groups that are present in lipids, for amide 1 and amide 2, that are groups that are present in proteins and chitin, and also bands that correspond to polysaccharides, mainly beta-glucans. These are, of course, the main components of this biomass. The spectrum of optimal sample presented some band shifts in comparison with the raw biomass. However, the most noticeable changes were observed when comparing the optimal sample to the spent brewer's yeast cells. There were some bands which disappeared. For example, the 1585 band and the 1346 band. Some bands became more intense, and there were also some band shift. Overall, the spectrums confirm that there are indeed spent brewer's yeast cell walls in the sediment that we collected after sample processing. That was the aim of the assay. Also, the beta-glucan content of the yeast cell walls was determined using Megazyme yeast and mushroom beta-glucan determination kit. After performing the steps provided by the kit, the results showed 41.3% of beta-glucan, which again confirms, according to the present literature, it's a pretty standard content of beta-glucan. So it confirms once again that we obtain indeed yeast cell walls. To assess the antioxidant activity of the spent brewer's yeast extracts, we used potassium ferricyanide reducing power and the PPH radical scavenging methods. Both methods show that the least concentrated sample, the 6.2% spent brewer's yeast sample, samples were indeed those with the highest antioxidant activity in comparison to the highly concentrated sample. However, FRAP showed a more comprehensive difference between the samples in comparison with the PPH, meaning that we observed that at an optimal temperature of 50 degrees Celsius, the antioxidant activity was the highest. There is a descending trend of antioxidant activity when the temperature is increased at 33 duty cycle. Things are rather different with the 50% duty cycle, since the antioxidant activity seemed to rise along with the temperature. Okay. We also assessed the antioxidant activity of spent brewer's yeast cell walls. Using the same methods, the trend of the samples was the same for the both duty cycles used according to FRAP assay. Also, using the PPH method, we obtained an optimal of 50 degrees Celsius for the highest antioxidant activity of the spent brewer's yeast cell walls. And to assess if there are any bioactive compounds such as polyphenols that can be retained during the brewery process on the surface of the cell wall, we performed the total polyphenol content of the spent yeast cell walls. And the highest polyphenol content was obtained when using the optimum conditions, the optimal sample of 6.2%, 40 degrees Celsius, 33 duty cycle. A statistical analysis is very useful for this kind of samples to provide a more detailed overview of the data. So we performed the Pearson correlation and heat map using SPSS. First, the Pearson correlation were performed between the samples from the spent bureau yeast extracts, and we observed that, for example, disruption efficiency is not really correlated with any other assay. The of antioxidant activities are significantly correlated with the burette results, and also the DPPH and FRAP methods are correlated, which means they have the same trend. We also performed the Pearson correlation association with the heat map for the samples of spent brewers yeast extracts along with spent brewers yeast cell walls, and we didn't obtain many correlations this time. However, a FRAP of spent brewers yeast cell walls were correlated with the burette assay, as well as the antioxidant activity of spent brewers yeast cell walls by DPPH and of spent brewers yeast extracts by FRAP. The rest of the correlation are mostly positive, so they follow the same trend, and there is only one correlation that is slightly negative. Thank you for your attention. If there are any questions.
Thank you, too. No? Okay, thank you. For the next presentation, Eliza Gabriela Bredfeld, please. We have 10 minutes. 10 or
I will try to be
yes,
fast.
please. Thank you.
Thank you for the nice presentation, and thank you for pronouncing my name right. Yes, today I will be presenting about the CO2 issue. The main, all the human activities bring pollution to our planet. Even all the sectors, the energy, the households, the agriculture, and even the wars. Wednesday, Mr. Wancha said something about the phosphorus from Russia that we cannot provide anymore. Unfortunately, they use it for something else, phosphorus bombs. Also, the wildfires bring hard pollution to the planet, and we had a lot of it this year. The main pollutant is the CO2, not because of its toxicity, but because of its high content, because we constantly release it. Why CO2 is so undesirable? Because it retains the heat from the sun, and it doesn't permit the excess temperature to go back to be reflected in the universe. The extra heat has a lot of negative effects for us. We have extreme weather, we have biodiversity loss, we had the sea level rise due to the glaciers meltdown, we have new pests, we have new disease. Here are some photos from this year's calamities when we have wildfires, droughts, and floods. Let's imagine an extreme scenario when the last human on the Earth meets a friendly alien around. The alien is surprised why it's nobody here. The answer of the man is, man, it was a gas. So we will try to find some solution in order to help and slow down the global warming. One solution can be the CCUS method. sorry. One solution can be CCUS concept. I don't know why it doesn't stay. When we, how the name it says, the carbon is captured, utilized, and stored. The main, the animation is joking with me today. This concept comes with another help, because we not only just capture the CO2 and store it in geological formation, but we also can use it for another domain, such as agriculture, food industry, construction industry. Therefore, I can underline the purpose of this study when we have a specific circular bioeconomy example. We capture the CO2 from the various sources. We capture it using a chemical solvent, from the green chemistry, the eutectic solvents. We will talk about it later. Then we biofixate it using the microalgae. After harvesting this biomass, we can use it for value-added products and again reuse them. So we have a closing the loop cycle. Why microalgae? Because they have a fast growing rate and they can use the unorganic carbon and transform it into organic form. The main nutrients are the phosphorus, the nitrogen, and the carbon. Therefore, the algae will be very helpful for us. Deep eutectic solvents are the 21st century solvents. They are green ones. They are composed using a hydrogen bond, where we have a hydrogen bond acceptor, in our case choline chlorine, and hydrogen bond donors. In our case, in our specific study, monoethanolamine and ethylene glycol. The solvents can be categorized by their number of components. The binary solvent from which we start, it was ethylene, made from choline chlorine and ethylene glycol. But our study didn't help us. The results on CO2 capture wasn't so attractive. Therefore, we functionalized it by adding another component, monoethanolamine, which is very known for its affinity for CO2 capture. We had an integrated installation where we started from an absorption column when the CO2 was absorbed using several deep eutectic solvents. The enriched solvent then was transferred to the desorption column when we apply temperature and vacuum in order to desorb the CO2, and after that, bubbling it in the bioreactors. I don't see it. And bubble it in the bioreactors periodically in order not to acidify our growth medium. The selected microalgae was a chlorella species from Niva Institute. Results, the first part of the results. As I told before, ethylene hasn't, we tried two main working parameters. With high pressure and room temperature, we had good result, an interesting result, and the greener working parameters with a slightly increase of temperature, but atmospheric pressure. An industry man would not like the 60 bars pressure, no. The results on the greener methods weren't so attractive. Therefore, I added monoethanolamine. We had a ternary solvent. We applied again the green methods, and the result was surprisingly good. We are between the interval of above. just by heating it a little bit. Another solvent I studied was a binary, but just exclusively with monoethanolamine and choline chloride. From several optimization, this molar ratio was the optimum. We had a very good absorption result, but this isn't a really big surprise because we had high amount of monoethanolamine, which in time will cause some problem, just like the classic method with aqueous monoethanolamine solution, because it has high volatility and corrosiveness. For the biofixation part, we use the two solvents with monoethanolamine. Compared to the control group, we had supplementary development of the microalgae. We studied two main parameters: optical density using UVB spectrometer and gravimetry for the biomass determination. As we can see, for the optical density, the ternary solvent had better results, and for the biomass, quite the same. Our study presents a promising approach for CO2 capture and biofixation using functionalized deep eutectic solvent and microalgae cultivation. This is an innovative method that really has potential. Future perspectives, obviously optimizing the solvents, new parameters for the culturing. Also, we can have economic viability. We can help for obtaining carbon credits and carbon certificates. And also would be nice to promote around the world and also some education. Thank you for your attention.
Thank you, Eliza, for your nice presentation. If are there any questions, please.
What are you intending to do with the microalgae after your process?
Oh, well, for microalgae in our team, we use them as fertilizers in agriculture, in biostimulants. This is our direction, but they have various uses because you buy spirulina and chlorella from from Tei Pharmacy. I saw it can be used to prepare biscuits, foods. Their potential is very high. And biofuel, we know we have a team with biofuel.
Okay, thank you.
Thank you very much.
So the last presentation, analytic fingerprints of selenium stimulated cabbage biofertification, will be presented by Ștefan Ovidiu Dima.
Good afternoon. I will try to present now some physical chemical perspectives of plant development while concentrating on particular analytic fingerprints of specific analytic methods. First of all, let's take a look at the plant cell wall structure. Plants contain two types of plant cell wall. The primary cell wall can be seen as as a dynamic pectocellulose hydrogel stabilized and expanded by turgor pressure, followed by exocytosis. Actually, the primary cell wall is stabilized by the turgor pressure and water accumulation, water and nutrients accumulation leads to the expanding of the flexible primary cell wall, while combining with the pre-built vesicles, they build the by exocytosis, they enlarge the primary cell wall. The secondary cell wall does not need turgor pressure since it is based on rigid macromolecular polymers like cellulose, lignin, glucomannan, and xylan, which are intercalated as we can see in the right. We use the two types of two doses of selenium biostimulant treated by foliar fertilization on cabbage, and we compare the samples by XRD analysis. First of all, we compare the cabbage sample. We can see it's a convoluted signal between cellulose, lignin, and pectin, with cellulose 1 alpha as the main signal. Actually, this is the first XRD fingerprint. Regarding the structure of cabbage, firstly reported as as cellulose 1 alpha and pectin. The difference between cellulose 1 beta and 1 alpha, 1 beta is consists in two chains monoclinic arrangement, and it's more resistant, while cellulose 1 alpha is one chain. It's more flexible and can be related to the edibility aspect, being also metastable and degrades quickly easily than cellulose 1 beta. Further, we correlate the diffraction spectra of all samples with the soluble fibers and insoluble fibers content, and the ratio between the soluble and insoluble fractions increased significantly for the inner leaves and correlates with the crystallinity. The crystallinity being correlated with a higher cellulose 1 alpha, respectively insoluble fibers. The infrared spectroscopy can reveal particular absorption bands. In this case, we compare the cabbage treated with dose 1 with red, with bacterial nanocellulose as representative for 1 alpha cellulose, pectin, and lignin. Specific for pectin are the COO bonds in esterified pectin, which we found also in cabbage samples. While for cellulose is related to structural carbohydrates and carbohydrates. If we compare now the control with the two dosages, we can see in the free hydroxyl bonds that the signals decrease, which suggest less free hydroxyls, and the bound hydroxyls increase, which suggest carbohydrates accumulation, and more hydrogen bonds involved in stabilizing and biofortifying the structure. Also, the signals around 2900 corresponding to carbon hydrogen in aliphatic structures due to their sharp shape. Actually, we also see that the band corresponding to esterified pectin decreases with the increasing of dosage, which suggests that the selenium biostimulant stabilizes the cabbage in the pectin in a non-esterified form. Also, the carboxyl and structural carbohydrates bands increase, suggesting biomass accumulation. the two bands for esterified pectin and free carboxyl groups can be used to evaluate the degree of methyl esterification by a ratio between the areas, and we can quantify or semi-quantify in this case, the decreasing of the degree of methyl esterification from 50 to 8 for the second dosage. Also, for the inner leaves and for the outer leaves from 61 to 22. Thermogravimetrical analysis allow the evaluation of the sample based on the thermal decomposition into specific fragments. In this case, we compare the cabbage sample with the degradation of pectin with onset temperature around 224, cellulose with an onset temperature around 329, and lignin around 340 or 400. And based on the derivative thermograms, we can divide the the thermal interval between 25 and 525 into 7 thermoregions, which we can assign to low molecular compounds like volatile organic biocompounds, followed by larger molecules, polyphenols and amino acids, which agglutinate together and transform into soluble fibers and proteins, and further in pectin and cellulose. We can see by through the overlay of this spectra that we have a faster transformation from low molecular compounds into pectin and cellulose for the second dosage. We can also evaluate the weight losses on each thermoregion, and we also see a faster transformation from low molecular weight compounds into pectin and cellulose. We can also use the residue in nitrogen, which correlates with lignin and cellulose content, and while the residue in air correlates with the mineral accumulation. And we can see on the last column, we have minerals accumulation stimulated by this biostimulant. The main conclusion is that the foliar tested selenium biostimulant induced a faster growth in plant metabolism, which can also correlate with a faster carbon dioxide sequestration, plants being the best systems for carboxyl dioxide sequestration. And thank you for your attention.
Thank you. If there are any questions? Thank you, video. Now we have a short coffee break, and then we'll see the selected posters presentation. So please invite us.
We have a surprise session for the invited posters. The posters shown yesterday and in the first day of the conference were evaluated by our scientific committee. And after each session, we sent some invitations. Most of you responded positively. So we have today, I think, 14 posters to be presented. The first one is Ionuț Octavian Zăuleț with the work Comparative Assessment of Marble and Granite Specimens Exposed to Climate Cycles. The full list of authors: Claudiu Eduard Zizescu, Ionuț Octavian Zăuleț, Rodica Mariana Ion.
Hello, my name is Claudiu Rizescu, and today I'm going to talk about our work, comparative assessment of aesthetic parameters of marble and granite exposed to climatic cycle. Marble and granite are some of the building materials widely used both as structure element, but they are mostly known for their aesthetic properties. Most of the old buildings have elements made of marble and granite, which are, when marble is exposed to outside elements, both day-night cycle or freeze-thaw during winter, they will suffer weathering, various kinds of weathering, consisting of loss of adhesion, loss of color, or disintegration. In order to protect this building against this weathering, first of all, we must understand the weathering effect, the weathering process. For this, we selected 3 types of marble available, widely available in our country, and 3 types of granite of different colors and different finishes. We exposed these samples to various processes, to various artificial weathering conditions. First, we exposed them to 20 freeze-thaw cycles, and we exposed them to 20 thermal cycles in the climatic chamber, which simulates the day-night cycle and the difference between day and night, which affect these materials. We analyzed their aesthetic parameters, their gloss, and we also analyzed them under microscope. In the table, we presented the difference in the chromatic parameters. We can see that marble, it's affected more by thermal cycles than granite, and their gloss, it's also affected. The change in gloss is most notably consisted in the loss of gloss, which may be due to the micro cracks and micro fissure that appear on the superficial surface. However, the changes in both in color and in gloss are very small, and which is somewhat usual, expected for natural material. In order to understand better this process, I think more cycles must be done so we can be able to observe a greater degrees of degradation. This is it. Thank you for attention.
Thank you very much for your presentation. If we have any questions from the room, yes.
What about the porosity before and after the treatment?
Porosity of all material was very, very small. It can be seen in the freezing coefficient that we measured after freeze-thaw cycles, that sample that's not changed much their porosity and their internal structure. They are not porous material to absorb high amount of water and suffer a high degree of effects after freeze thaw, such as mortar and concrete, which are porous and will suffer considerable effects.
Thank you.
You're welcome.
If we have any other questions from the room or from the online participants. If not, thank you very much.
You're welcome.
I forgot to mention that the judges of this section will be our foreign guests. So please pay attention to their questions.
Now we invite a young researcher, Andrea Miron, to present us advanced adsorbents materials for remediation of contaminated waters with heavy metals by enhanced adsorption mechanism.
Good afternoon, everyone. My name is Andrea Miron, and today I will present my poster. So everyone knows heavy metal in water is a significantly environment problem. Heavy metals such as copper, nickel, zinc are present in surface water. So it's necessary to develop a new strategy to absorb this heavy metal, and alginate and zeolite are the best candidate for this absorption process. The technology present in this work, it's very simple, and we necessary just two steps. The first one is the homogeneous of the zeolite in the polymeric solution, and after that the forming of the beads in a calcium chloride solution. First, I would like to speak about the characteristic of the beads. In the first picture, we see the FTIR spectra, and in the both sample, we can see the characteristic peak for the alginate, and in the sample with composite, we can see the cyan group, a characteristic for the polyacrylonitrile, sorry. The next step is the thermal degradation. This presents the thermal stability of the sample. We can see the beads with composite material have a higher stability compared with the beads with zeolites. To attest the capacity of the absorption of the sample, it's necessary to have the preliminary test. The first one is the solid liquid ratio, and the second one the pH test is. So we can see in this graph the best solid liquid ratio was 1.5 and the best pH was 5. The next test was the selectivity for nickel and copper, and we can see a best affinity for copper compared with nickel. And the last one test, we see the kinetic study of the sample. I used two different kinetic models, pseudo first order and pseudo second order. We can see here we have good results for the pseudo second order. That means we have chemical absorption of the materials. And in conclusion, we can talk about this material are good for copper absorption of from water sources. Thank you.
Okay, thank you. If you some question? Okay, the next presentation.
Thank you. The next presentation, it's Sorin Fiorel Dolana with the work polyurethane-based environmentally friendly polyols as a promising alternative to HTTP binder for composite propellant rockets.
Hello.
Composite propellants are used extensively in anti-hail rockets and also in military applications. We aimed to solve the environmental problem that arises by using hydroxyl-terminated polybutadiene, or HTPB, as a binder in their formulation. For this, we compared the HTPB with polyurethane formulations based on commercial polyether polyols and a novel green polyol synthesized in our laboratory by chemical recycling of PET, polyethylene terephthalate. We also used glycerol as a cross-linking agent and castor oil as both as a cross-linking agent and as a plasticizer, being a trifunctional polyol. From the tensile tests, we can see that the majority of polyurethanes based on commercial polyols and green polyols had considerably larger Young's modulus and also performed better in terms of tensile strain and stress at break. The best performing one had a Young's modulus of over 5 times that of HTPB. The FTR revealed the chemical structures that we expected. All the polyurethanes had peaks associated with carbon-nitrogen and nitrogen-hydrogen bonds. The commercial polyether polyols and the green polyol had carbon-oxygen-carbon ether bond that we expected, while the HTPB had unsaturated carbon-carbon double bond. The thermogravimetric analysis revealed 2 main decomposition steps that, according to literature, are associated with the breakage of the urethane bonds, the first decomposition step that occurs at a lower temperature, and the second decomposition steps, the step that occurs at a slightly higher temperature, is associated with the destruction of the polymeric backbone. We can see that HTPB had a very high second decomposition step, while the first step was close to the others. The polyurethane made with our polyol, our green polyol, had the first step was in agreement with the other polyols, but the second step was slightly higher than the commercial polyols. So we can conclude that HTPB can be successfully replaced, at least for these tests. We will test them with help of our partners, Military Technical Academy. After we will assess the glass transition temperature, they will put in a model rocket and they will test them. Thanks.
Thank you, Sorin. Any question? Okay. Now for the next selected poster presentation, we invite Ioana Silvia Hosu to present us processes for preparing peroxynitrite electrosensitive deposition and methods for selective detection.
Yes,
okay.
Could you see my screen? Can you hear me, or can you see my screen also?
Okay.
Okay, so good morning, everybody. My name is Ioana Silvia Hosu, and today I will be talking about processes for preparing peroxynitrite sensitive deposition and methods. Do you hear me? Because I don't know if you hear me.
We can see the poster, maybe. You can put.
Yeah, I have the small presentation. You see? Do you see it?
Nothing.
Okay, just a second. Okay, I'll do it. Okay.
Yeah, screen. Share screen.
Yeah. Okay, perfect. I think now you can see it.
Thank you.
Okay, sorry. So today I'll be talking about processes for preparing peroxynitrate electrosensitive deposition and methods for selective detection. So my work is concentrated mainly on screening biostimulants. So we will start with a small definition of biostimulants, with the scientific context, with the objectives and strategy, and the electrochemical sensors prepared for screening these biostimulants, conclusion and small perspectives. So a biostimulant, in fact, it is any microorganism or any substance that could increase nutrition efficiency in plants. And this can occur by stimulating plant metabolism, reducing impact of abiotic stress, or improving crop yield. And this kind of composition, named biostimulants, come in very good accordance with the bioeconomy and climate change initiatives that we should follow. The problem is, in fact, that biostimulants are mainly composed and produced by hazard that can lead, in fact, to very unwanted results and very bad plant growth, as opposite to biostimulants that could be created by design, that could also mean very good results with optimal plant growth. So why do we need, in fact, biostimulants? We need biostimulants because of the green gases, the temperature extremes, the UV radiation that can lead, in fact, following to drought, flooding, bleaching, heavy metals accumulation in soil, and so on, that could lead after to increased leaf temperature, stomatal closure, reducing germination, and some other effects because of several causes in the end. And one of the main causes is reactive oxygen species production and oxidation of biomolecules. So the thing is, a biostimulant has many mechanisms that could help us improve the qualities of plants. And one of these is increasing tolerance to this reactive oxygen species production. In fact, and my work is regarding the most important reactive oxygen species named peroxynitrate. That is an anion similar to a radical synthesized in plants by the reaction of nitric oxide and superoxide with a near diffusion rate constant. This anion can be detected usually in a spectrophotometry using 302 nanometers wavelength, but the problem is that this method is not fully selective and sensitive enough. So my project here, in fact, presents a method that constructs biosensors based on screen-printed carbon electrodes that could help us further screen between different biostimulants. Shortly, if you have a good biostimulants, the concentration for the calibrated sensor for peroxynitrate will decrease. And if you have a bad or not so good biostimulants, you will have a higher signal. I will also confirm this method using fluorescence, and I will validate biostimulants in the order I succeed to screen them with the sensor by growing some Arabidopsis plants. So what are my methods? I'm using mainly cobalt phthalocyanine and other metal center phthalocyanine to modify the screen-printed carbon electrodes by electropolymerization in different ranges, and drop casting. I will characterize these prepared electrodes by different physical chemical characterization and other electrochemical characterization. Here, for example, in the middle, we have a electropolymerized polycobalt tetraamino phthalocyanine screen-printed carbon electrodes with a different number of cycles. That can lead to this mechanism presented on the down right slide. So first, I studied this peroxynitrate reduction using cyclic voltammetry with the presented electrode-deposited polycobalt phthalocyanine tetraamino screen-printed carbon electrodes in presence and in absence of peroxynitrate. And we can observe with red that we got some oxidation around 0.2 volts and some reduction around minus 0.1 volts in this specific window and this specific scan rate. I went further and studied different possible peroxynitrate interference studied in the selected range, and we had no real influence. For the calibration, I have been chosen cyclic voltammetry in the specific range with different concentration. I have them in a calibration curve, and I have chosen also the other methods, more sensitive ones, more precise one, as chronoamperometry, with the same sensor presented at minus 0.3 voltage, for example, in this case, and I calibrated the sensors. Here I'm trying to say how I compare different electrodeposited, one electrodeposited sensor and drop casted sensor, and I reached the conclusion that as a metal center, manganese is the best one, but I still have to study the other polyelectropolymerized phthalocyanine. And I can conclude that the methods and the processes I presented today can work for screening biostimulants. I already applied for a patent application, and I would like to acknowledge the founding organization for my postdoctoral research project. And I would also like to thank you for your attention, and sorry for not sharing the screen in the right moment.
Thank you very much, Ioana.
You're welcome.
Objective reasons, she couldn't be here with us today, but have a safe trip, and we expect you home. So if
Thank you so much.
Questions from the room or from the online participants? If not, thank you once again, Ioana, and I invite the next speaker, George Mihail Teodorescu, with the work, the mechanical, thermal, and nanomechanical properties of composites made of bio-based polyamide and ash powder.
Hello, everyone. Thank you very much for the opportunity to present my work today. So the objective of this work was to assess the effectiveness of ash powder as a reinforcing agent in bio-based polyamide 1010. As we know, the world tends to grow very interested to more greener pastures regarding petroleum-based polymers. And so bio-based polymers are a rather good alternative for petroleum-based synthetic polymers. And so today I want to show you the effect that fly ash, a waste material, has on bio-based polyamide 1010. These two materials were processed in dynamic conditions through melt processing methods such as extrusion and injection molding, and were characterized by mechanical analysis, dynamic mechanical analysis, thermal and nanomechanical analysis. And from the viewpoint of mechanical analysis, the rigidity of polyamide 1010 is increased with the addition of ash powder up to 16% at the maximum concentration of ash that we added. The dynamic mechanical analysis showed an increase for the TG of the composites compared to bio-based polyamide. And this indicates an improved viscosity for the composites as a result of the good adhesion between the filler and the polymer matrix. Thermal analysis showed a very slight decrease regarding the temperature at the maximum rate of decomposition for the composites compared to the polyamide. And also in the case of DSC analysis, the melting temperature also sees a slight decrease for the composites compared to the neat polyamide. The SEM imaging shows the surface of polyamide 1010 and how clean it is, but it also helps us to better indicate the presence of ash powder in our composites. As you can see, if you look really hard, you can see the cubic structures present in each composite. But these large cubic structures are also joined by smaller particles. And through the help of EDX spectra, we saw that the elemental composition of this powder matches the oxidic composition of the ash that we determined before starting this investigation. And so this proves that the ash is present within the polymer matrix. Now, from the viewpoint of nanomechanical properties, nanoindentation showed a increase of reduced modulus and hardness for the composites compared to bio-based polyamide 1010. And even though we have a decrease in the elastic recovery of polyamide 1010, this increase in properties, it correlates well with what we've determined earlier regarding the mechanical properties. And so our materials become rigid when we introduce this ash filler in our polymer matrix. We also see an increase in surface roughness and for the coefficient of friction, meaning that the composites are more resistant to scratches. And so we noted that from this investigation that the introduction of ash powder in the polyamide 1010 through extrusion and injection molding leads to an increased rigidity of the composites. But also we require further investigations in order to improve other properties, such as the mechanical property, the impact strength, and the elongation of our final composites in order to find an application in some industry for these materials. And so I would like to thank you all for your attention.
Thank you, George, for your nice presentation. A lot of results. Very nice. So, any question? No? Okay, thank you again. The next presentation will presented by Lucian Gabriel Zanfir with assessment of biogenic amines in food production products and their detection using nanocomposites based electrochemical biosensors.
Hello, my name is Zanfiu Lucian Gabriel, and in this poster I will present a study carried out by our group regarding the isolation of biogenic amine producing microorganism, as well as the detection of biogenic amines putrescine and histamine using electrochemical biosensors, and their use as indicators of food spoilage. Different food products were processed and inoculated in growth media. The resulting cell cultures were analyzed using microscopy and Malditov mass spectrometry techniques. Thus, 15 biogenic amine producing microorganisms were identified, such as various gram-negative enterobacteria and various species of yeast associated with the spoilage of foods and beverages. After the identification of the microbial species, electrochemical studies were carried out using electrochemical biosensors. Screen printed carbon electrodes were modified with nanomaterials based on single wall carbon nanotubes and the redox media, the Prussian blue. These were used for the electrochemical detection of hydrogen peroxide resulted from the enzymatic oxidation of the biogenic amines by mono or diamine oxidase. Electrochemical studies were carried out on the sensors using the cyclic voltammetry and amperometric techniques. The sensor modified with the nanomaterial showed high sensitivity for the reduction of hydrogen peroxide. For the preparation of the biosensors, the enzymes diamine and monoamine oxidase were immobilized by entrapment in sol gel and chitosan polymeric matrices. And they were used for the detection of putrescine and histamine in the food samples. The results obtained in the electrochemical measurements were correlated with those obtained in the biological studies. Thus, it was observed that the highest concentrations of histamine and putrescine were detected in the spoiled meat samples, as well as the fish ones, where a variety of biohygienic amine producing microorganisms were identified. While for wine samples, for example, no biohygienic amines were detected due to their antimicrobial properties. In conclusion, biogenic amine producing microorganisms were isolated from various food samples, and nanomaterial based biosensors with single row carbon nanotube and Prussian blue based nanomaterials were used for the detection of putrescine and histamine. Thank you for your attention.
Thank you very much, Lucian. I must tell you that your work was highly appreciated by the scientific committee, as we have many votes for your poster to be presented today.
Thank you very much.
If there are any questions from the room or from the online participants? If not, thank you once again. And I invite, before inviting the next guest, I must tell you all that the speakers are invited in the order of poster registration, so is no other reason behind it. So the next speaker is Violeta Carolina Niculescu with the work Removal of Organophosphorate Herbicide, Assorption onto Nanosilica.
Hello, sorry for my voice. I'm a little influenza affected. I'm coming from Râmnicu Vâlcea, from National Institute for Cryogenic and Isotopic Technologies, and I'm at this moment working in nanomaterials laboratory. Today I'll present some preliminary results that we obtained for removal of an well-known and well-used herbicide, glyphosate. And for this, we use nanosilica that we prepared, but to obtain better results, we functionalized the material with aminopropyl groups. In order to see the quality of our materials, we perform several structural morphological analyses, and the presence of carbon, oxygen, and nitrogen in our materials was confirmed by elemental analysis and EDS. As you can see, in amino material, we have a concentration of around 6% of nitrogen, confirming that the functionalization was achieved. Also, the FTR spectra confirmed the appearance of aminopropyl vibration and the specific surface decreased radically from around 600 for the raw material SBA3 to 14 square meters per gram in the amino functionalized material. The SEM morphology showed spherical and spheroidal particles for the materials. Sorry again for my voice. The glyphosate absorption was monitored photometrically by determining total carbon and total phosphorus content in two solutions that we prepared according to the solutions that every agriculture used, and also for concentration that was found in wastewaters. As you can see, after 90 minutes, an equilibrium of absorption was achieved, and this was the time for our that we taken into consideration for our Langmuir and Henry modulations. And we saw that pseudo second order kinetics in Langmuir isotherms was the better model that confirmed us that the absorption rate dependent on absorption capacity and not on concentration of the adsorbate. As a conclusion, we also performed some FTR spectra, and we saw that glyphosate functional groups were present within the pores of our aminosilica materials. In conclusion, a quantitative absorption and a complete recovery of the adsorbent was observed. The absorbent being regenerated and can be used for at least 5 cycles. At the end, I want to acknowledge our financial support by Romanian Ministry of Agriculture and Development, but also Romanian Ministry of Research, Innovation and Digitalization. Thank you for your attention, and excuse my voice.
Thank you, Violeta, for your nice presentation.
Thank you.
Any question? Okay, thank you.
Thank you.
We invite now Cristina Firincă to present us screening of autochthonous microbial strains for the bioremediation of heavy metals.
Greetings, everyone. I will briefly present our results in regards to the screening we have conducted on autochthonous microbial strains for the bioremediation of heavy metals. Heavy metals are persistent pollutants that tend to bioaccumulate along the trophic web, exerting various levels of toxicity onto all forms of life. Conventional treatment methods have the disadvantage of being laborious, costly, and damaging to the environment. Therefore, more environmentally friendly and efficient methods need to be studied and implemented. In that sense, the aim of our research was to isolate and identify indigenous metal-tolerant microbial strains for the purpose of removing chromium, lead, and zinc from contaminated environments. We have successfully isolated 7 bacterial strains and 10 fungal strains from contaminated soil. The majority of them displayed high tolerance to lead and a high sensitivity to chromium and zinc. Fungi displayed overall higher tolerance to the 3 heavy metals compared to bacteria. We have further selected 1 strain from each group that presented tolerance above the moderate level to the 3 heavy metals for the bioremediation assay. The removal efficiency was determined by comparing the concentration of the heavy metals in solution before and after the microbial treatment, These differences were detected using commercial screen-printed electrodes modified with different materials. For chromium detection, Prussian blue mediator was precipitated onto the nanopaste of the screen-printed electrodes. For zinc detection, multi-wall carbon nanotubes were used in pair with Prussian blue and chitosan. And for zinc detection, was used for lead detection, excuse me, was used the polymetric matrix containing gold nanoparticles and chitosan. The screen-printed electrodes presented high sensitivity that allowed us to observe that the fungal strain presented significantly higher efficiency in reducing the concentration of chromium, lead, and zinc in solution compared to the bacterial strain. The fungal strain, identified as Trichoderma longibrachiatum, reduced the concentration of zinc and lead in more than 50% and more than 80% of the concentration of chromium. Future studies will focus on optimizing the bioremediation process in order to be extended into the field. Thank you for your attention.
Thank you very much, Christina. If there are any questions from the room, if not, I have one. No, I have one question. Did you evaluate the fate of the metal after the uptake? What happens to the metal?
We conducted more analysis, meaning Fourier transformed infrared spectroscopy and SEM analysis that showed us that the metallic ions adsorbed onto the surface of the fungal cell, as well as intracellular adsorption. So the heavy metals were stored for a long period of time intracellularly and extracellularly, and this is a good indicator for future uses in field tests.
Thank you. Are any more questions from the room or from online? If not, thank you. We'll go to our next presentation. Roxana Madalina Stoica, studies on biosurfactant production by two Pseudomonas species using substrates from agro-food industry.
Okay, hello everyone. First of all, I would like to thank you for the opportunity to present my work today, entitled Studies on Biosurfactant Production by two Pseudomonas species using substrates from agro-food industry. We all know that microbial diversity represents an important research field in the biotechnology industry because it countless new genes and biochemical pathways to explore enzymes, polysaccharides, biosurfactants, antibiotics, or other useful molecules. Biosurfactants are important bioactive compounds produced by different microorganisms belonging to the Pseudomonas genus, Bacilli, Corynebacterium, or other species, but according to the literature, the Pseudomonas species are mainly used to produce these important byproducts. In recent years, the use of waste substrates in production of biosurfactants represent an area of interest for researchers. So the purpose of our study was to investigate the ability of two bacterial strains, Pseudomonas putida and Pseudomonas fluorescens, which belongs to our culture collection of microorganisms, to investigate their ability to produce biosurfactants using cheap substrates like whey and corn extract, which are byproducts from agro-food industry. Because the actual production of biosurfactants is limited today due to the high cost of components of media used in fermentation processes. So regarding the cultivation of bacterial strains, we were achieved 3 steps characteristic for a microbial bioprocess, such as pre-inoculum preparation on solid media, inoculum preparation and bioprocess, which was also on liquid media, which contain the same ingredients like inoculum preparation, with whey 3% and corn extract 2%. The bioprocess condition were taken at 30 degrees Celsius for 7 to 72 hours. And with an inoculation volume of 10%. So the biosurfactant production was based on the measurements of emulsification index, which was calculated by multiplying by 100 the ratio between the height of the generated emulsion and the total height of the mixture. So the results that we obtained were very good. At the end of the bioprocess, the supernatants obtained was evaluated for their capacity to emulsifying the sunflower oil, heptane and octane. We obtained the best good results of the emulsification index with values over than 70% in both cases with both strains. So our results demonstrated that both Pseudomonas strains were efficient in biosurfactant production and using cheap substrates from agro-food industry. And our study will, these are some preliminary results. Our study will include the purification of biosurfactants, optimization of the media, characterization through high performance liquid chromatography, and testing their capacity against some phytopathogens of crop plants. So this is my presentation. Thank you for your attention.
Thank you very much. There are any questions from the room or from the online? Oh, sorry.
No. No, until now, no. No. Yes, we will do this. Yes, thank you.
Thank you. If there are any more questions? No, thank you. Our next speaker is Elisabeta Irina Geană with the work using forest biomass to contribute to population health and ensuring sustainable environment.
Hello, my name is Elisabeta Irina Geană, and thank you very much for the opportunity to present our work here in front of you. Today I will present the work using forest biomass to contribute to the population health and ensuring sustainable environmental. As we know, current societal challenges include the transition to the circular bioeconomy through the valorization of agro-industrial waste into byproducts for satisfying the numerous societal needs, but also the transition to the energetic system to assure the climatic neutrality and resilience. In this context, forest biomass represent the most important biomass in the form of primary biomass or secondary biomass resulted from the wood industry. And also the forests are used for the airborne leader in order to monitor the atmospheric contamination, but also is an important source of carbon sequestration. And recently, the forest biomass was used to be transformed in the biofuels, which lower carbon footprints. So in this context, our aim was to transform the agro-industrial waste, including here forest biomass, into the bioproducts in the circular bioeconomy system. And firstly, we start with the extraction of bioactive compounds in order to be used for the development of products for health application. Next, the transformation to the biofuels, including bioethanol, with low carbon footprints and low greenhouse gas emissions, but also the mobility to the energy system by developing the mobility vectors like biohydrogen, biomethane, and heat-an to sustain the transition of the energetic system to climate neutrality. In these posters, our first step was to propose the valorization of forest biomass in the form of needles of bark of soft wood species into bioactive extract, which will be used for application in wood helling application. But also our purpose was to review the literature publication related to the transformation of forest biomass into the mobility vectors, biohydrogen, biomethane, and bioethanol. For the experimental parts, first we use surface response methodology in order to optimize the microwave extraction parameter, like ethanol concentration, microwave power, extraction time, and the ratio of solid to solvent ratio, in order to obtain polyphenolic extract with high content of polyphenols. The resulted extract were characterized by quantitative UVV spectrophotometric methods and also by UHPLC-MS for quantification of some bioactive compounds or identification of the others. The bibliometric study was conducted based on the Web of Science database associated with the main keywords with forest biomass, energy, forest biomass, and biofuels, forest biomass, and bioactive compounds under the period of 2014 and 2023. Bibliometric analysis was conducted using the GVOS software. The surface response methodology was conducted using XLStat software and indicate us the optimum parameters in order to obtain the high polyphenolic content extracts. The main quantified bioactive compounds in the extract were flavonoids, and the representing compounds was catechin, which was quantified in important amounts in needles and bark extracts. Also, due to the high performant liquid chromatography coupled with high resolution mass spectrometry detection, we identify some important steel bands like astringin, pisiatanol, isoharfortigenin, which shows important bioactive antioxidant properties. And also in our previous work, we demonstrate the wood helling properties of this extract. Integrated biorefinery of forest biomass involves firstly the extraction of bioactive compounds for health applications, followed by the pretreatment of the resulted biomass by physically, mechanically, or chemically pretreatment methods of the lignocellulosic material and then saccharification and fermentation in order to obtain biofuels like bioethanol, biomethane, biohydrogen, biomaterial like bioplastics, polylactic acid, polylactic acid, polymethylene terephthalate, but also chemical compounds like sorbitol, lactic acid, succinic acid, and others. From the bibliometric analysis, the forest biomass was related to the bioactive compounds, was used to obtain the different extracts with health application, but also the extracts were used to obtain different silver nanoparticles with antimicrobial and antibacterial properties. The literature studies conducted until now indicate that the forest biomass is an important source for the development of the energy vectors like bioethanol, biohydrogen, and biomethane. But also there are a lot of studies conducting the life cycle assessment of the transformation of this biomass into the biofuels. The most studies are conducted to transformation of forest biomass into the bioethanol and biogas, and less for biohydrogen and methane. So we can affirm that lignocellulose biomass has considerable potential to solve the environmental and energy crisis through the transformation into the biofuels in order to replace the fossil fuels, which are the main source of global warming. In the conclusion, intelligent exploitation of forest biomass by obtaining the bioproducts in the circular bioeconomic system intend to ensure the health of the society and the population, but also on the environment, represent an important way toward the climate neutrality and resilience. I would like to acknowledgement to the financial support to our nuclear program in our institute through the project Cascade Valorization of Agro-Industrial Waste of Plant Biomass Type in Bioproducts with Value Added in Circular Bioeconomy Systems, but also to the institutional project. And thank you for the attention.
Thank you very much. If we have any questions from the room or from online, if not, thank you very much. This concludes this session, and I would like to our foreign guests to cast their votes. In the meantime, we will take approximately 1 hour and 50 minutes break for lunch, and during this time, they will also vote. Thank you.